Very good morning, one and all. Welcome to my channel. This is Reciprocity Theorem. Dear students, today we are going to start with Reciprocity Theorem. Before this Reciprocity Theorem, we have completed Superposition Theorem, Thevenin's Theorem, Maximum Power Transfer Theorem, and Norton's Theorem. Norton's Theorem and Thevenin's Theorem were the dual of each other. Recently, we have completed maximum power transfer theorem, and we have seen that how much popular Thevenin's theorem is. Why? Because before going into application details of maximum power transfer theorem, we were actually applying Thevenin's theorem across the load terminals of the circuit given for maximum power transfer theorem analysis across the load terminal A and B. Now we are going to start with next set of reciprocity theorem, that is reciprocity theorem. The reciprocity theorem deals with what happens to a response when the position of source or excitation in a loop or in a circuit is changed. It means what? Basically it deals with the behavior of response or the nature of response or the magnitude of response, or in a very simple language, what happens to response when the position, the place of excitation or source, simply voltage place is changed, interchanged inside that circuit only. The statement is the reciprocity theorem deals with or states that in any linear active bilateral single source network, please mark it, this should be single source network. That should be a single source network. That should be a single source network. The ratio of excitation to response remains same when the position of these two are interchanged. The position of response and the excitation. Excitation means this is your source, which is giving you excitation in the circuit. It is the source, that is voltage source. See this, these are the two typical circuit diagrams. This is number 1 and this is number 2. What we are going to observe? We are going to observe that in this active linear bilateral single source network, this is single source, no source other than this V voltage is present in this circuit. You can see, you can observe this. Okay, all the elements are here active, linear and bilateral. It should be noted down very clearly that it is having linear and active bilateral elements, and it is of course single source network. If this is all satisfied by a circuit, a network, then we can interchange the position of voltage to its response. Initially in the circuit diagram 1, see this, I is the current response flowing across Z4, and V is connected in loop number 1. Now we are going to interchange. This from here and this from here. See this, call it I dash and call it V. This is V. Now according to reciprocity theorem, I dash will be equal to I. Okay, I dash will be equal to I. It means what? It means what? The ratio of excitation to response remains same. Whatever the ratio of excitation to response was in circuit diagram 1, it will be same for circuit diagram 2. Okay, let us move towards its proof part. Dear friends, we have two circuit diagram here. See this, number 1 and number 2. This is 2. This is first. This is first. Okay. And this is second number of circuit diagram. Here I have applied transfer impedance method. Okay. This is your Vs. This is your response in one of the loop, that is IR, and this is your entire circuit network, which is active, linear, bilateral. Of course, it is active, linear, and bilateral. What we are interested in, we are interested to find out what happens to the response when the position of these two response and the excitation source is interchanged between them, among them. Okay, let there be only source Vs. There is only source Vs. It is clear, this is only source. This is only one source available or present in this circuit diagram 1. Now, response R is given, IR is given by IR is equal to Vs into delta SR by delta Z. By transfer impedance method, we have ZSR, that is ZSR is equal to delta Z by delta SR, which is equal to Vs upon VR, which is equal to Vs upon IR. ZSR is equal to delta Z upon delta SR is equal to Vs upon IR. Let us connect a source voltage VR. Let us connect a source voltage VR in Rth loop. Let us suppose this is Rth loop, and we are connecting a source voltage VR, the Rth loop. This is your Rth loop, and we are calculating response in Sth loop. This is your Sth loop. This is your loop number S, that is Sth loop. So, the response in S loop, that is Is equal to given by I is equal to VR into delta Rs upon delta Z. Now see this, Z transfer is equal to ZRS is equal to delta Z upon delta Rs, we have seen, which is equal to VR upon Is, which is equal to VR upon Is. These all are coming from transfer impedance method. Now, if VR is equal to Vs, let us suppose if VR is equal to Vs, then delta Rs is equal to delta SR, and the ratio of excitation to source remains constant. That is, Z of SR is equal to ZRS. That gives Is is equal to IR. That is, the response in Sth loop is equal to the response in Rth loop. Hence, we have proved that. The reciprocity theorem statement that when a circuit is active, linear, bilateral, and having only one source, then the ratio of excitation to the response remains same when these two are interchanged. These two means the excitation, the source, and the position of the response and the response. Now there are some important points to remember. That is, important points to keep in mind regarding the reciprocity theorem. what is that? Point number 1. You can make note of this. In this theorem, the position of any passive element, position of any passive element that is R, L, C does not change. Does not change. You can remember by putting a cross mark over a position of RLC. Position of RLC. Position of RLC or passive element present inside that circuit never changes. Point number 2. What is happening in point number 1? In addition, only source and response is interchanging. I am putting a big smile. By this big smile, you can remember that only the position of source, yani excitation, and the response is interchanging. This is a big smile. So big smile is actually giving you idea that the position of source or excitation and the response are interchanging among themselves. Point number 2. The impedance matrix for two circuits remains same if we does not change the selection of loops. It means what? If loop selections are not changed, that implies impedance matrix remains same. That is, impedance matrix remains same. Impedance matrix remains same. Point number 3, which is very important. Impedance matrix is symmetrical about its diagonal elements. Impedance matrix is symmetrical about its diagonal elements. Now let us come to its limitations. Limitations means where it fails to apply its upper boundary. Point number 1, which is very important, which is applicable to single source network only. Applicable to single source network. It is applicable to single source network only. Okay. Point number 2. When there is dependent sources available, in the circuit, it fails to apply. It fails. This is the question for verifying a reciprocity theorem. In this question, we are to verify reciprocity theorem. We have just studied what reciprocity theorem is. We have also calculated, we have also gone for its proof. The statement of reciprocity theorem states that in any active linear bilateral, I am going to repeat these keywords, in any active linear bilateral single source network. It is single source network. So our question is containing, the question which we are going to deal with is containing only single source. So it is valid question. And what about those parts which is actually linear active bilateral? So the resistors, the capacitors, the inductors are linear active bilateral. Okay. There are no diodes, there are no something else which could violate our active linear bilateral components. And the statement of the reciprocity theorem. The ratio of excitation to response must be equal to same when it is interchanged. The response and excitation is interchanged. And please keep in mind, other than the excitation or source and the response, nothing else is interchanged. Okay. So let us just start with our network. This is your, let us say this is I1, this is I1, this is minus, this is plus, this is plus, minus, this is plus, minus, this is plus, minus, and in loop 2, let us have some different color to understand. This is loop 2. In loop 2 we are having current I2. This is plus, this is minus, this is plus, this is minus, this is plus, this is minus, this is plus, and this is minus, and this is your current I. This is given in the question. This is the response given in the question. The response given in question. Now what we are going to do, we are going to apply KVL in these two loops respectively. Apply KVL, that is, in the first loop, that is minus 10 I1 minus 6 I1 plus 6 I2 minus of J8 I1 plus minus J8 I2 plus 50 angle 30 degree is equal to 0. Now let us observe that while writing this Kirchhoff's voltage law, I have gone from in opposite direction of current flow. That is, I have gone from in this direction. Okay, in this direction I have written the I have written the KVL equation. Okay, you are actually free to choose any directions you can actually write in the direction specified by current I. So nothing matters. There is nothing much bigger deal that why I have started writing from minus 10 I1. I have started writing from minus 10 I1 because I am moving from here to here. I am moving from here to here. Okay, minus 10 I1 minus 6 I1 plus 6 I2. Okay, now simplifying these equations actually. So it is I1 16 minus J8 plus I2 minus 6 plus J8 is equal to 50 angle 30 degree, which is your equation number 1. It is equation number 1. Okay, now coming to loop number 2, that is in this one. See this. This is the equations. I am going to write equation for this loop. So let us write minus 8 I2 minus J10 I2 minus 8 J8 I2 minus 6 I2 plus minus J8 I2. It is actually I1 plus 6 I1 is equal to 0. This implies I1 6 minus J8 plus I2 minus 14 minus J2 is equal to 0. By solving these two equations, applying Cramer's rule, we have I2 is equal to I, which is equal to 1.862 angle 333.45 degree ampere. This is your I2 or I. Therefore, V by I is equal to 50 angle 30 degree upon 1.862 angle 333.45 degree is equal to 26.852 angle minus 330.45 degree. Now what we are going to do, we are going to interchange the position of the excitation and the response. Means we are going to interchange this one. So the circuit will become like this. Circuit will become like this. This is your excitation, that is voltage source. V is equal to, the value remains same, 50 angle 30 degree volt. This is 8 ohm, this is J10, this is 6 ohm, this is J8, that is minus J8, this is 10 ohm, and this is your I. This is current I1, this is current I2. Now applying sign convention, this is plus minus, 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 this is plus and minus. Okay. By changing position of V and I, we have changed the position of V. See this, V and I. We have changed the position as per the statement given by the reciprocity theorem. Now, by solving Cramer's rule, we can have that the first statement, the first KVL equation, I1 minus 16 plus J8 plus I2 6 minus J8 is equal to 0. And from the second one, from the loop number 2, that is I1, this was from loop number 1, this was from loop number 2. So I1 minus 6 plus J8 plus I2 14 plus J2 is equal to 50 angle 30 degree. From Cramer's rule, we are having, that is I1 is equal to, the value of I is equal to 1.862 angle 333.45 degree ampere. So the ratio V by I is equal to 50 angle 30 degree upon 1.862 angle 333.45 degree, which is coming 26.852 angle minus 330.45 degree. Hence what we have seen, that V by I ratio remains same, and the reciprocity theorem is